Hello, everyone, and thank you for being here. I'm very happy to be able to speak to you because I like to share the work I do in science. I think that's the best way to improve it, and also because of the distinguished list of speakers that have preceded and will go after me. So you understand what I'm going to talk about. I'd like you either to think of a child as the one in the photograph on the screen that either has hearing problems that are very great, or they may be even hearing problems that are very subtle. This child in particular, we put him, but he didn't have a severe hearing problem. Later on, he had difficulty in interacting with his friends, with his family, with the teachers, and the question is, can this be avoided? And we think so, because it's due to a problem in the brain, and problems in the brain, if we find them early enough, can be dealt with. Now consider the little girl in the top upper left of the figure. She's having difficulty understanding the teacher. Why is this? Is it because she doesn't hear well? Or is it because she can't concentrate and have attention? Many of these cases are also due to problems in the brain, and we think they can be avoided. Finally, who doesn't have a grandmother or a grandfather or somebody in the family who starts losing his memory? And this is known as mild cognitive impairment. Later on, as it advances, there's the terrible disease called Alzheimer's disease, where the person loses all memory and can die quickly. This is also a problem of the brain, and we believe it can also be prevented. To understand how serious this problem is for the world, I show you on the screen a diagram prepared by the World Health Organization. This is known as the global burden of disease. What is the burden of brain diseases on humanity? And how is it measured? It is measured by the disability-adjusted life years. What does this mean? That if in a country people live until they're 60 and they die before, then they've lost the years of life. But then if they do survive until 60, then if they live with a stroke, with dementia, then they live less than a full life. And that means that they've lost part of their lives. So there, in the diagram, in the smaller circle, you see when 1% of the life of people are lost. And in the larger circle, you see when 10% of the full brain life of people is lost. You see in the cyan color the areas of the world that have high income. You see with the orange color the areas of the world where there's poor income. These are lower middle income countries. Now, one thing that's interesting here is that this is the percentage of life lost. So if you look at it, it is precisely in the countries that are poor, that have less medical facilities. This is where people are losing most of their brain lives, which is essential for their countries. And I think this is an imperative. We have to try to find ways to detect early brain disease and to facilitate that these countries can deal and help these people. And that is what I've dedicated about 50 years of my life to work on, which is to look for technologies, for techniques that allow the detection early on of all the conditions of the brain that I've said. So to understand what I'm working on, we all know that the brain has billions of neurons. And there you see one neuron conducting electrical activity to signal or talk to another neuron. These neurons are connected through chemical transmitters chemicals that go from one to the other and produce changes in the currents. Here in the next figure, you see a simulation. This is from my friend Sean Hill from the Blue Brain Project. In one of the biggest computers in the world, they simulate the activity of billions of neurons. Now, all these currents produce electrical activity on the surface of the head. You saw there that we can put electrodes, and then we can record potential differences. And these potential differences are the curves that you see at the bottom, known as the electroencephalogram or EEG. Now, the EEG was discovered this year, 100 years ago, by the German scientist Hans Berger, who was so unsure of what he was doing that he waited 8 years before publishing. Those are the first recordings you see on the bottom. And on the left, when the person closes his eyes, there's a cyclical activity of waves. These are brain waves that occur once, 10 of them in each second, known as the alpha rhythm. And this alpha rhythm, or Berger rhythm, was a great discovery, very difficult if you think that the size of these voltages is in the order of a millionth of a volt, 200 million times lower than the electricity that you get in your house. So one first aspect was the development of technology. And here you see the device that Hans Berger used. And here, that is me, a much younger version of me when I was 20 years old. And we're working with the first Cuban computer developed at the same time as in Japan to be able to store the electroencephalogram in the computer and use mathematical techniques to analyze them. That is later what at the Cuban Center for Neuroscience, of which I was the founder and the first scientific director, is a state-of-the-art device around the year 2000. Here we see the work that I've been doing here with Professor Dejong Yao at the University of Electronic Science and Technology, developing modern technology. However, it is not enough to put the EEG in the computer. We have to find out about it, and for that we use mathematics. And my work was inspired by the famous Norbert Wiener, who was an American scientist who developed the theory of cybernetics, but more importantly, he applied a discovery made by Joseph Fourier that you can decompose any signal like the EEG into different frequencies. And this is known as frequency or spectral analysis. So basically, once again, we see the device that we developed. You see on the right the EEG. This is recorded from one of our subjects. Here you see the frequency analysis, and what you see is a curve of how much energy there is at different frequencies. And that arrow shows you the alpha rhythm, which we can now measure as a number. On the bottom right is neuronal tomography. This is a technique I developed around the year 1995, and for the first time we showed the famous Berger or alpha rhythm, that it originated, where you see it at the part of the brain that has to do with vision. Here I show you then a work that we did in Cuba, which was to look at healthy subjects from the normal population and study how the alpha rhythm and other rhythms changed from birth until 95 years. And this is the average that you're seeing now. This is a map, that's the average map for 300 normal subjects. Recently, from the University of Electronic Science and Technology, we completed this map, which is the same for 9 countries across the world and more than 2,000 subjects, and we're increasing. With this, we have a map against which we can compare normal subjects. Now, to compare how far someone is from the normal map, we need to have a concept of distance. And the distance is not the simple distance, let's say, that one can walk in ordinary space. We have to use a concept known as Riemannian space. And this is a mathematical concept that if the measurements we make are, for example, in the gray curve, then measuring the white line from one point to the other is not the correct distance. It's the longer distance that goes through where the information is. It's the curve. If one has normality at one point and a patient at the other, the correct way is to measure it all along the ribbon that you see there. Now, this is important because it allows us to combine Fourier analysis with measuring the difference between normality and a patient. And this work was based on the work of Riemann, who in the 19th century developed the theory and said, maybe nobody will use this because it's too abstract. But in fact, just a few years later, Albert Einstein used it to formulate the general theory of relativity. And now we're combining it with Wiener's idea of Fourier analysis of the EEG to measure patients' differences. Now, all of this sounds very abstract. Is it useful? Here is a study that we carried out on Alzheimer's in the country of Colombia, where a friend of ours had detected 5 families that had a mutation, that with this mutation, people at 45 years would have Alzheimer's. We were able to find these maps that allowed us to know who in the family had the mutation without having to do genetic analysis. This is just one example of how we can use the electroencephalogram to detect early disease. On the other hand, in Cuba, we developed the Audex. This is a device that in newborns allows you to see if the brain is responding to sound. And with this device, we were able to screen since the 80s children at birth for hearing loss. And we showed the earlier you detect a problem, the better is the school performance. Then we developed a device. This is Infantix. We're working on it together with USTC, not only for audition, but for vision. Importantly, we showed that this can be done in any country, not only a country with a good health system like in Cuba. And in the country of Ecuador, we were able to help Ecuador to screen 500,000 children at birth to see if they'd have hearing loss. Finally, I have to say that the electroencephalogram also helps with children that have learning disabilities. This is when we test children playing a game, and then when they have the activity marked by the arrows, they lose attention. So if we treat this type of very subclinical epilepsy, then we can improve the children's performance. From nature, we have this view that everything is linked from before birth until old age. And there are things that improve your brain health and diminish your brain health. One study that we did which illustrates this is in the country of Barbados. They had hunger for children at the beginning of the 70s. And there you see 2 children, one that had protein energy malnutrition and another that not. We have been fortunate to be able to study these children for more than 50 years, the same people. This is an experiment that we carried out. We did it from China, but went with Canada, Cuba, and the US to Barbados. There you see we're studying the children. And what we found is that the children that had malnutrition in the first year of life had learning disabilities, and there you see how their brain was altered, and had also later, now that we looked at them only a few years ago, a lot of problems in their learning. They might be dementia. So the words of Xi Jinping inspires us, and it is in essence that we have to collaborate between countries and improve science and technology to make a shared and common future. For that, we have created the Belt and Road Laboratory between the University of Electronic Science and Technology and the Cuban Center for Neuroscience, and there already you see the countries of the Belt and Road that have joined us already in the Global Brain Consortium. We believe that what I showed you at the beginning, which is the great global burden of disease for humanity due to brain disorders, this loss of potential for all people, it can be reduced, it can be solved. It needs to be, for medical systems and health systems to be improved, but it also depends on the work of the scientists to produce technologies that can be used worldwide to benefit humanity. Thank you.